here are three differentiation results. If you differentiate x to the power something, the n exponent jumps down and the new x power is 1 less than before. To differentiate products, you use the product rule. The derivative of the product of two functions becomes y prime is the first function's derivative times the second function plus the first function times the second function's derivative. Similarly, if you have a quotient, to differentiate it, you use the quotient rule. If y is one function over another, y prime, the derivative is given by this big fraction where the top is the old top function's derivative times the bottom function, as it is, minus the top function times the bottom function's derivative, all divided by the old bottom squared. I emphasize that to differentiate a product, you must use the product rule. Let's find the derivative of a couple of things. First, here, y prime will be 3 times 7x6, and in the same way as the 3 hangs around, the quarter is just going to hang around. It's 0.25 if you like. X differentiates to 1, pi being a constant on its own differentiates to nothing. So y prime ends up being 21x6 plus half a copy of x minus 7. And of course, with experience, you don't have to go through this middle step. Okay, so since we know how to differentiate x to the power of something, in a situation such as this one, we first rewrite our function in a suitable way. So we combine these guys into this, and you rewrite your function without root signs. Now we take a new line and find the derivative function. And of course, if you want to, you can give your answer like this. Same thing. Here we have a product, so we can use the product rule to get y prime the derivative. First function's derivative times the second function as it is, note the brackets, plus the first function as it is times all of the second function's derivative. Note the brackets, and that is blah blah blah. You can simplify it. Of course, alternatively, you could have started your solution by expanding stuff out and then differentiating it. You get the same answer. Here, you can use the product rule, but a quicker thing to do is to notice that you can rewrite the thing you want to differentiate at x to the power of 4/3. Hence, let's find that derivative on a new line. So the prime symbol, the dash symbol, indicates differentiation. And as usual, the 4/3 will jump down and the new x power is 1 less than before. Here you have a quotient, so you just use the quotient rule. Note that I begin the solution by saying w prime x is blah blah blah. I don't just write down this. This is a function. The derivative is a function, just like any other function. So up here you have the top function's derivative, all of it, times the bottom as it stands, minus all of the top, times all. Again, I emphasize that you need to put out the brackets. And we divide everything by the bottom squared. Here is an extremely important fact to know by heart and to keep in mind. It is not in the formula booklet, and again, you want to keep it in mind. If you get stuck, ask yourself, can I use this fact? Which says that the rate of change of f at a point x equals the value of the derivative at that point, and also the slope of the tangent line to f at that point. So these three, rate of change at the point, the derivative, and the slope of the tangent line to f at that point x, they are equal to each other. Here's a question about rate of change. This is the graph of fx is x squared plus 3. So it's x squared moved 3 steps up. Anyway, first we're asked what's the rate of change of f at 2. Now in theory you can use two approaches. Either you look at the tangent line and calculate this slope through rise of the run, but algebra is simpler, quicker, and more accurate. So use algebra if possible. So here we just use that the rate of change at the point is equal to the value of the derivative. So we want f prime 2. This is found in a two-step process. First you find f prime x is 2x. Then you take a new line and evaluate it at your point of interest. So the answer to the rate of change question at this point is 4. But note the two-step process. Same story with 2.4, so you just evaluate the derivative at 2.4. The third part is about average rate of change in an interval. So we start here at -1, 4, and you end up where x is 2.5, so here. And the y-coordinate is of course found by plugging in it, so you get 6.25 plus 3, so 9.25. Now, what's the average rate of change in this interval? That is done not using calculus, but just using school maths or common sense. So you just take the change in the value of the function and divide by the length of the interval. The end value is 9.25, the beginning value was 4, and the length of the interval is of course 3.5 for us. So here you get 5.25 over 3.5, or if you like 21 over 14, so 3/2. So memorize this important fact. Tangent lines. In this exercise, fx equals x cubed plus 5 over x, and the domain is the set of positive numbers. Find the equation of the tangent line to f at 2. At x is 2, so at 2. So we look at the formula for tangent lines, which you should know by heart, or it's in the booklet. Anyway, y minus the value of f at a equals the value of the derivative at a times x minus a. So for us, a is 2. That's what this means. We want the tangent line where x is 2, so a is 2. That is the beginning, so you just take the formula and replace all the a's by 2. We get y minus f of 2 equals f prime of 2 times x minus 2. And now it remains to find these two guys numerically. F of 2 is found in a straightforward manner. You just plug in 2 into the function, you get 8 plus 2.5, in other words 10.5. F prime 2 is found in a two-step process. First you find the derivative as a function. So f prime x, well of course x3 differentiates to 3x squared. What about this guy? Well, it's 5 times x to the power minus 1, and now the minus 1 can jump down, and the new x power is minus 2, and if you like you can write it like this, the derivative. Now you take a new line and evaluate the derivative at your point of interest, in this case 2. So anyway, we get 12 minus 1.25, so it's 10.75. So this guy is 10.5, this guy is 10.75. So we get y minus 10.5 equals 10.75 times x minus 2. Now when you give your answer, ideally you move this term to the other side. So y is 10.75x. Here you have minus 21.5, so you move this guy over, you get this, which is the answer for the equation of the tangent line to f at 2. Since it's the equation of a line, it's natural that the answer has this form. 2 is now trivial. What's the slope of the line? Well, you just look. What is m? M is 10.75. That's the slope of the tangent line. Which also reminds us of this fact here. Anyway, the third part of the question was about sketching graph of f as well as the tangent line. So, to do this, we have fx is x cubed plus 5 over x. We create a table of values, so some positive x values. Remember, the domain was the set of positive numbers. The corresponding y values, the values of your function. Then you plot the points in the plane, you connect them with a smooth curve, and that will give you a sketch of the graph of your function. That's the red one. Here is the point where x is 2, and remember the y coordinate was 10.5. And I drew this tangent line. It's the line touching the graph at this point. But when I drew it, I used that it was the line with slope 10.75 and y-intercept minus 11. That concludes that exercise. As a side note for the interested student, I will mention, because maybe you're curious, what is this bottom point? How do you find this bottom point? What is the x-coordinate of this bottom point? Well, to answer that question, we will discuss this in more detail later on this term, but the key is to use that the rate of change is described by the derivative. So you're going downhill when the derivative is negative, uphill when the derivative is positive. So at this bottom point, the derivative must take the value 0. Now for us, this was the derivative, which can be factorized like this, and therefore the x-coordinate of the bottom point is the 4th root of 5/3, or in other words, if you use a calculator, approximately 1.14. But the main thing is that you know how to use the formula for tangent lines. This one over here. Just find A, find these numbers, and put things together.